Hi everyone, welcome to my Module 3 presentation. So today I'm going to be talking about a logistic regression, which is a predictive analysis used to describe data, explain relationships, and predict an outcome. So the main distinguishing feature of a logistic regression is that the outcome of interest is going to be categorical. And while comparing it to the standard linear model, while they're both ways to analyze data, a logistic regression is a generalized linear model, whereas it differs from the standard linear model, which is a general linear model. And they also differ in a few key ways. So while the main goal of both tests is to predict the outcome variable, in a logistic regression, the outcome, as I said, is going to be categorical, whereas in the standard linear model, the outcome is going to be continuous. So instead of predicting values as you would in a linear regression, a logistic regression is going to estimate the odds of a certain event occurring. Additionally, the output is going to be a little different. So the output is going to range between 0 and 1. As you can see here from the graph, they both form two different shapes. So a logistic regression would form this S-curve, and a linear model would produce a line of best fit. Additionally, a logistic regression uses maximum likelihood estimation to predict the outcome, with the idea that the observed data would be the most probable data. And in a standard linear model, we would be using a least squares estimation to estimate parameters and minimize residuals. So when you're looking at the assumptions, they're pretty similar too. In both cases, you'd want low multicollinearity and outliers, but specific to the logistic regression, the y variable does not need to be normally distributed as it does in a linear regression, as it's only two values, 0 or 1. So now we're going to look at our demo. As Press and Wilson noted, we should be using a logistic regression since we have a qualitative response. However, we are going to run it through the standard linear model to compare and contrast. Friedman also noted in his paper that you need to know the connection between the model and the phenomena you're studying. So here we've laid it out. The outcome variable is going to be a binary variable with the values of 0 or 1 for making it to the playoffs, 0 being not making it, 1 making yes, 1 being yes, making it to the playoffs. Additionally, for our categorical variable, we have chosen 5 out of the 8 NFL divisions with the most Super Bowl wins. So 5 divisions means 5 levels of our categorical variable listed below. And additionally, for our continuous variable, we simply added the total points scored in the final 5 games of last season. We've also included an interaction term in our model to help explain the outcome. With the interaction term, we're looking to see if there is a combined effect of the two predictors that explains more of the outcome variable that they would as just individual main effects. So because of this, our variables will need to be centered to allow for interpretation and avoid issues with scaling. So we can move on to visualizing our variables, and they're normally distributed, which is a good sign we can keep moving forward. Centering the variables makes them more interpretable. And because this is a linear transformation, it does not change the relationship between the variables. The purpose is to allow us to resolve some issues with scaling because of the interaction term that we've included. So it's important to note that we would have non-essential multicollinearity before centering, but once we've centered it, we get rid of the non-essential multicollinearity, and all we're left with is the essential multicollinearity. And now that we've taken care of our continuous variable, it's time to deal with our categorical variable. And we want to see how the data can be recoded so that we can create comparisons at different levels of our variables. So choosing what type of coding scheme you use really depends on your model, what questions you want answered. Each type will really affect your interpretation, so it's important to be really intentional when you choose what kind of coding scheme you want to use. So we'll start with dummy coding, and since we've assigned each division a number 1 through 5, we could do dummy coding by pre-selecting one division to be the reference group or the comparison group. So this will give us deviations from the reference group and produce contrasts between each level and the base level. The reference group would be coded 0 for all of the code variables, which would make it the 0 explicit in dummy coding. So in our model, all divisions would be compared to the NFC East, which serves as the reference group by default. However, this is not super useful for our purposes, so we're going to need to recode. We can look into unweighted effects coding next. In unweighted effects coding, estimates use the grand mean, but the process kind of allows for similar comparisons to the dummy coding scheme, but there is still a reference group. So this produces contrasts between levels, but the 0 is implied. However, we have an uneven number of teams who participated in our research, meaning we have an unequal cell sizes. So this can lead to issues with differences in variance in unweighted effects coding, and to counter this, we are going to kind of decide on weighted effects coding instead. So instead of reflecting a comparison to the reference group, we will be changing it to reflect a proportion of the contrast. Therefore, the weights will reflect differences in cell frequencies for each of the effects. So the weighted effects coding gives us estimates that are deviations from the grand mean and also centers our variable for us. So overall, the main difference between all of these is the points of reference, and we will be using the weighted effects coding for our division. Next, we ran this through a standard linear model to see like what the results would be. So we used our centered variables and our weighted effects coding, and this is not at all the diagnostics you'd expect to see from a standard linear model, and it tells us we've probably misspecified our model. So since the linear model assumes a rectilinear relationship, this is not suitable for our data. And because we've misspecified our model, we need to kind of think back and reflect and decide what regression analysis would be best to use for our model. And since we have a binary outcome, we should be doing a logistic regression as mentioned by Press and Wilson. So let's go ahead and run the diagnostics for the logistic. And that looks a lot better. It's more what you would expect to see for a logistic model. So we can go ahead and look at the summary table. So what we're looking here is log odds. So if X increases by 1 unit, the log odds of Y increases by K units when the other variables are held constant. So first we can look at the intercept, which will be the weighted mean of the log odds for all divisions when the LS total is equal to its mean. So the intercept is significant. So we know that the log odds of all groups are significantly different from 0. And then when we dig a little deeper into the P column, we can see what else is significant and what that means for our model. So our alpha is set at 0.05, and for main effects, we are looking at deviations from the grand mean. Additionally, these are partials since it's a multivariate model. So what we're really looking at is the unique variance accounted for by that specific division, excluding the others. So we have no significant main effects of division. So division alone does not explain a significant amount of unique variance in the team's likelihood of making it to the playoffs. There is a significant effect of total points, showing that there is a unique variance explained by our continuous variable. Next, we have our interaction. So we have one significant interaction in this model. So for the most part, division does not appear to be to significantly moderate the relationship between points and making the playoffs. However, for Division 2, which is the AFC East, the interaction is significant, meaning that there is more variance in this particular level explained by this interaction, and we can reject the null of no relationship. So next we're going to look at the regression coefficients. For division, the regression coefficients represent the difference between the grand mean of the log odds and the average of winning for each division. So it's important to note that the LS total is held constant at its mean when calculating these. Next, we have our estimates are logic coefficients, which tell us the relationship between the predictor and the outcome, where the dependent variable is on the logit scale. So these estimates tell us the amount of increase in predicted log odds of making it to the playoffs that would be predicted by a 1 unit increase in last season's total score, holding all the other predictors constant. So the average effect of a team's points scored leads to a 0.0987 increase in log odds of being in the playoffs. So the standard error here is similar to what we see in the standard linear model, and by dividing the parameter estimates by the standard errors, we can get our z values. And the reason we have z's instead of t's is because we have for a binomial outcome, the variance depends on the mean and not the residuals. So down here we have the deviances, which test whether the independent variable provides statistically significant explanation. And because our residual deviance is lower than our null, then we can see that our predictors did help explain more of the model. Next, we have our AIC, which is most commonly used in comparing models and kind of is similar to an adjusted R squared, in that it's a penalizing factor that accounts for the number of variables we are using and the number of observations we have. Lastly, we have our Fisher score, which tells us the number of iterations used to fit the model, and ours is 4, and we have this because it's based on a maximum likelihood estimation. So moving on to our odds ratios. So log odds are super confusing to interpret, so we're going to look at them through the lens of odds ratios. So here we have our odds ratio column, and then these are our confidence interval columns. So the odds ratio represents the constant effect of a predictor on the likelihood that an outcome will occur. So how to tell if there's a significant relationship. So to have significance, we want to see that the range between these two columns does not include 1.0. So for the continuous predictor here, it does not include 1.0 because it starts above and ends above. So the average effect of LS score on odds of being in the playoffs at its mean of the reference group is significant, and the average effect of the LS total score increases the odds of being in the playoffs by a factor of 1.10, which pretty much means that the odds of being in the playoffs are increased by 10% for a unit increase in LS total score. And then when looking at the interaction between Division II and LS total, it is significant from the output table from the slide before, but as if you could remember, it's barely significant, it's barely under 0.05, it's at 0.043 or 44. So that can explain why the last column is just over 1, but if it was rounded, it would be 1 flat. So it's right on the cusp of being significant, similar to the output. So when you're comparing the outputs, this side by side, you can kind of see the estimates decreased from the linear model to the logistic, and the standard errors increased, which makes the t or z value decrease. And again, we have z's because it's a binomial outcome, and the variance depends on the means and not the residuals. Additionally, you can see that the p-values changed, and we found the interaction to be significant in the logistic, but not in the linear. So if we're looking at this, this is a plot of our data, and these are just a few examples that we're going to dig into a little bit later. So here we have our examples and we have our output. So what we did, we made 0.5 as the cutoff for making it into the playoffs or not. So the Philadelphia Eagles, who scored 97 points in the last 5 games of their season in the NFC East, which is division number 1, which is the red line, gave them a 0.67 probability of making it to the playoffs, which is a positive since it's above 0.5. And if we look into our crystal ball and read the future, we do see that in 2021 to 2022 season, they do make it to the playoffs. So they are a true positive. Moving on to the New York Giants, they scored 77 points in the NFC East, which is the same red line. So you follow it down to here and you get a 0.31 probability of making it to the playoffs, which is a negative prediction. And we look into the future and they did not make it to the playoffs. So therefore they're a true negative. The Kansas City Chiefs scored 122 points in the last 5 games of their season and have made it to the last 2 Super Bowls. So they're in the AFC West, which is the blue line right here, division number 4. This gives them a 0.94 probability of making it to the playoffs next season, which is a positive prediction, and they did, so that's a true positive. However, we do have the Seattle Seahawks, who scored 118 points in the last 5 games of their season. They are in Division 5, which is the NFC West, and that gives them a 0.9 chance of probability of making it into the playoffs, which is a positive predictive outcome. However, if we looked into the future, next season they do not make it into the playoffs, so they are a false positive. So moving forward, a few conclusions before we wrap up. It's important to remember that correlation does not cause causation, and conclusions drawn from regression are valid as a code or a system of equations, but not always transferable to the big picture real world type applications. So Friedman spoke to that in his paper. So everything we do, we have to take with a grain of salt. Additionally, we do have one significant interaction, but it's close, so we should be kind of alert for that and like looking out for type 1 errors in that case. Additionally, the possibility of false positive and negative, as we noted with the Seattle Seahawks, for big sports gamblers who are depending on our model to make their bets and make them money, this could be a real liability and you could lose them a lot of money. So we definitely would want to replicate our study, as Friedman said, so we can figure out if we can trust it or not. Additionally, sports statisticians may look into additional variables to include to improve the predictive power, such as passing yards, touchdowns, rushing yards, etc., just to add more dimensions to this model. Additionally, looking at other regression models may be helpful, just to see if we can explain the phenomena a little bit better. And thank you for a great semester, for a great class, for watching my module. And this is hopefully me partying at the pub when I get my module 3 grade back. Have a great summer, guys.